Hello everyone, my name is Alex Sanchez, and today I will show you the advance of my master research project at National Laboratory of Scientific Computation. Today I will talk about machine learning to predict antimicrobial peptide synergy with MetaFlow framework. I organized this presentation in 4 points. In the introduction, I will talk about antimicrobial resistance and establish the objective of this research. Then we will see the methods, we will see the workflows that we are using, we will discuss the results and set up the conclusions. So let's start with the introduction. Currently, we are facing the issue of antimicrobial resistance. We have a scenario where pathogens are becoming resistant to existing antibiotics, leaving us with fewer treatment options to cover them. In 2016, the World Health Organization estimates that antimicrobial resistance could cause 10 million deaths annually by 2050. 8 years has passed since that, but no significant advance has been made. In 2021, just few new antibiotics were approved for medical use. That is not enough to combat this problem. Now, in 2024, antimicrobial resistance is already one leading cause of death around the world. So, we need new and innovative strategies to combat this problem. One strategy is the combination of different antibiotics targeting the same pathogen. When combining 2 or more antibiotics, there are 3 possible outcomes. They have an additive activity, or they interfere between each other, leading to a loss of activity, or they have a synergistic activity where the pathogen inhibition is potentiated. This kind of combinations can be a powerful tool to combat antimicrobial resistance as they enhance effectiveness, reduce the resistance development, and requires less doses, minimizing toxic effects. However, due to the large amounts of possible combinations, experimental validation tests are not feasible. And here is where artificial intelligence comes. Artificial intelligence can learn from already known synergistic combination, can learn the patterns and predict if a novel and unknown combination can have this desired activity. So, the objective of this project is to predict synergistic combination between antimicrobial peptides and conventional antibiotics using machine learning models. But why antimicrobial peptides? Well, they gain attention in that selected due to their broad spectrum activity, the mechanism of action that target the cell membrane and disrupting it, leading to cell death, and recently they've been demonstrated to have intracellular targets, reducing the resistance development. Now, let's start with the methods. In our dataset, as we are using supervised machine learning, we have 2 pieces of information. We have our X vector that represents our input. In this case, we are using antimicrobial peptides, antibiotics, and microorganisms. Our target variable, represented by Y, that in this case, we are using the fractional inhibitory concentration index to label the target, distinguish between synergistic and non-synergistic combination, +1 and -1, establishing a threshold on this index. As features, we have several physical-chemical properties for both antimicrobial peptides and antibiotics. We also use manual inhibitory concentration as activity metric. For the microorganisms, we have the string information. In the model, we are using light gradient boosted machine classifier that have been demonstrated to outperform in a recent study. Before explaining the flows, I would like to highlight that we are using MetaFlow, that is a framework designed to create, manage, and trace machine learning processes. With this tool, we create a flow to download and format data from the database of antimicrobial activity and structure of peptides. We request the data from this database, format it. Then we extract the antibiotics names and use RTKit to calculate several chemical descriptors to then merge this information Standardize the activity value, the MIC value, label the information based on a threshold for FIC index, and one could encoding the microorganism information. The step flows generates the input for the train model flow, where we first split the data into train 80% and test 20%. The train data is used to feed a data scalar that contains standard normalization and principal component analysis for reduction to reduce dimensionality. We generate a fitted scalar, and then the scalar trained dataset is used for train the models. We are using ResRGB to model light gradient boosted machine models using hyperparameter tuning, across validation, and to calculate several performance metrics. The test dataset is first scaled with this fitted transformer, and then predictions are made using the best model selected by ResRGB, and we are using area under rock curve as method to choose the best model. We set up different experimental conditions for modeling. We select two different thresholds to label the target, use several different amounts of components for the dimension reduction, set up more than 600 hyperparameters during the model, and each one with a five-call cross-validation. This generates more than 32,000 models that who have experience with artificial intelligence knows that it's not easy to manage this amount of models, but thanks to the help of MetaFlow, all this was easy to set up and was easy to analyze. Now, let's start with the results. As I mentioned before, we are using functional inhibitory concentration index to label the target function into synergistic and non-synergistic combination, +1 and -1. This index takes in account the minimal inhibitory concentration of the agents alone and in combination. The lower index, the more synergistic is the combination. Starting at thresholds of 1.0, we have more entities in the positive class, so we also decide to explore another threshold of 0.5, where we have a more balanced situation. So let's start with the performance with a threshold of 1.0. We see in both cases that performance without the use of principal component analysis has the highest values, and also we see that area under rock curve has a significant decrease during tests that may indicate overfit problems. We also see that recall, that actually very good, is very high, but recall is based on positive class prediction that tell us that the models are actually predicting the positive class, the true synergistic, but the discrepancy between recall and area under rock curve may indicate that the models are biased on the positive class. We can see this better in these confusion matrices. We see that the true positive cases are very high, more than 90%. That is actually very good, very promising, but we need to improve the performance prediction on the other classes because that's also important. So we see that we have room for improvement and enhance our models. In the case of using a fixed threshold of 0.5, we see a more consistent metrics around all the models. We now can see more clearly that as the way we increase the number of components during principal component analysis, we see the attempt to increase the model metrics that indicating that the task for prediction synergistic is not so easy, and maybe we need another way to represent our information to improve the models. We also see that now area under rock curve has improved a lot, actually, that is very promising, but the decrease during tests and analysis indicates that we still have overfit that we need to solve, but the results are very promising. Using this threshold on FIG index, we see now that we have improvements to predict other classes, the true negative classes, that is very important. So we are seeing that the models are actually starting to learn the patterns, but again, we also need enhanced those models to generalize well on unseen data, as we see in this plot. So let's summarize our principal findings. We see the area under rock curve methods indicate that the models, even if if the performance is good, there is still need to take care of overfits. And also, we see that an increasing number of components during principal competence analysis, we see they are increasing the model performance. This indicates that actually principal competence analysis reduce the least correlated filters, but this is not enough to capture the important information, as we need other techniques, other embedding techniques to integrate this information. I would like to highlight that the use of MetaFlow framework allows to generate all these experiments and analyze them easily. Before finishing, I would like to thank the financial agencies of Brazil that supports this project, my research group at Laboratory of Informatica, and finally, the organization of this event. Thank you so much.